Okay, good morning, everyone. Welcome to our AI for You lab talk. My name is Xiaoshang. I'm the director of the Future AI Lab, AI for You. We are working on topics on reasoning, uncertainty, and ethics in the cross area of AI and Earth observation. And this is our usual seminar series. And today we have the pleasure to welcome Dario Oliveira, who is giving the lab talk today. And he's a guest professor in our future lab. And before he starts, I will briefly introduce him. So Dario received his master degree in 2009 and PhD in 2013, both in electrical engineering from the Pontifical Catholic University of Rio de Janeiro, Brazil. And he was a visiting scholar at the Institute of Superior Technical in Lisbon, Portugal, between 2008 and 2009. And he was also for some time in Germany, particularly at the Leibniz University of Hanover from 2011 to 2012. And as a postdoctoral fellow, he studied machine learning applied to neuroscience at the University of Sao Paulo, Brazil, and applied to dairy science at the University of Wisconsin, USA. And from 2015 to 2021, this is where we get in contact with Dario. He was working at the IBM research lab in Sao Paulo, Brazil. So we are very happy to have him join us as a guest professor specialized in the topic of reasoning. And today he's about to give us a lab talk, machine learning for unlabeled EO data. And this would be a good introductory talk to his research. And we hope that this will also stimulate collaborations between our guest professors and the other lab members. Okay, Dario, the floor is yours.
Okay, thank you, Xiaoxian, for the introduction. As I said, today I'm going to talk about machine learning for unlabeled EO data. And more specifically, I'm going to talk about machine learning approaches for sustainability challenges using scarcely labeled or unlabeled observation data. So the first thing is, okay, what about sustainability and Earth observation data? I selected this major project from the European Space Agency, which is called Earth Observation for Sustainable Development. And they state that satellite Earth information technology has a major potential to inform and facilitate international sustainable development work in a globally consistent manner. So it is a major topic. They have everything to do with each other. And they selected a few topics. And here in this presentation, I'm going to approach agriculture, forest, and climate out of these topics that they selected as topics of interest in this matter. So from a theoretical core research standpoint, my goal in this presentation is to approach this problem of the manual labeling burden that we observe in here data problems such as Earth observation problems. So a few years ago, when deep learning began to explode, we had this scenario where we had unsupervised learning methods, with, of course, by definition, with no labeling burden, but with very poor performance compared to supervised learning methods that had a good performance, but a high labeling burden. And usually we had this path where we had unlabeled data, then we tried to do some clustering, some whatever, that would drive us to a noisy labeled data, that we could do some curation to get high quality labeled data that could this one use these methods for at the time to have really good performance. But in the last few years, 2 or 3 years, then several different subfields raised in machine learning that are actually beginning to populate this path. So we have deep clustering, domain adaptation, self-supervised learning, weekly and semi-supervised learning, data augmentation, transfer learning, multitask learning, that are more or less this building blocks in this path between unsupervised learning and supervised learning that really enabled the performance that we used to have in supervised learning to be achieved with much less manual labeling burden. And then how that applied to Earth observation sustainability problems exactly. So here in this talk, I'm going to talk about these three topics: so the culture, climate change, and forest monitoring, and my personal experience with some of these subfields applied to these areas. So for agriculture, I'm going to talk about deep clustering and learning from label proportions. For climate change, I'm going to talk about specifically about weather generators. So I'm going to talk about synthesis using variational autoencoders and how can we improve the synthesis using prototypical regularization of the latent space in these models. And about forest monitoring, I'm going to talk about multitask learning and active learning, so we can have the mapping of individual tree species in the forest area with a very small training sets. So this is basically the outline of this presentation today. So first, I'll begin talking about agriculture, and I'll begin with deep clustering. So in this paper that it was just published at IGERS, we're basically evaluating different unsupervised deep clustering methods for crop classification using sorry image sequences. Then the basal approach that we had for that was a very simple one, which was basically using an autoencoder, getting the latent space representation out of these sorry image sequences, and then clustering these representations using k-means in a second step. But of course, there are fancier ways to do that, and we're comparing also with this method that was one of the first deep clustering methods. It's back from 2016. And it's called deep embedding clustering. And it basically has two phases. The first phase is actually the parameter initialization of network using a standard deep autoencoder. And then we have this step B, which is basically the clustering step, where we iterate between computing this auxiliary target distribution and minimizing the callback liability divisions to it. So basically what we have here is we have these two steps. One is the soft assignment. So it's this key ij in the bottom left part. And then basically we have the distance computed and the soft max of the distances. So zi is the feature representation of a given sample I, and mj is the centroid of a given cluster. And we compute the kj is a soft assignment of this sample zi to all the clusters that we have in our model. And then basically we get these soft assignments, we compute these soft cluster frequencies for a given cluster, and we make this frequency to follow a T-student distribution. And in this way, when we do that, we're basically clustering, we are having a centroid, and we're making the samples that are closest to the centroid to follow more or less this distribution. So we are in the end having a clustered latent space of our training set. And then later in 2020, there is this deep k-means method where they don't do this in two steps, automation steps, but they do this jointly. So they jointly cluster using k-means in the latent space, and they learn the representation altogether. And to do that, basically they have this loss that is a reconstruction loss as a standard autoencoder, and also this clustering loss, which is a slight modification of the one that we saw before. So we have here the feature h theta x is the feature of a given x sample, and we have this rk is a centroid for the case clusters, and we multiply that by a weight that is called this closeness function, which is basically an assignment cluster function. And this is again is a temperature scale softmax where they have this alpha parameter, but they can control between a hard assignment, which means that only the distances of the side cluster to that sample would count for the loss, and a soft assignment where we would have these values varying depending on the distance of the sample to each centroid. And then we apply that to to crop classification, and we have this data set that we usually play around with this data set. And this is a public data set from Brazil. We have, this is from Mato Grosso, which is a state in Brazil. And we have 14 images, Sentinel-1 images with V and VH colorization from October 2015 to July 2016. And we have 11 classes of MUs. But as you can see here in this chart at the right, we can see that we have basically two time series here, depending on plantation cycles. So the first one is from October to February, and it's basically the soybean cycle in Brazil, specifically in the center of Brazil. This is the soybean cycle. So we have mostly soybean planted, and we have soil in the other tiles. And then the second time series is usually from March to July. And then at this time, we have the cotton and maize plantation cycles. So basically, it's common that we have consider four classes. We gather all together these two time series in a unique training set. And then we have soybean, maize, cotton, and others, which are basically soil or pasture, but we get it all together as an others class. And then when we tested with these deep clustering methods, we got these results. Basically, they are not very encouraging. The encoder we were using at the time was not so good. Now it get even better results, a bit better results, but the relative results are more or less the same. So the supervised method with this encoder was around 70% of accuracy. And the best deep clustering method achieved 55%, which I mean, it's not irrelevant, but it's still far from what we wanted to have. And unfortunately, the fancier method was actually the one that got most confused in one of the classes, and the performance was not so good for that. It was confounding a lot cotton with actually the major class, which is soybean. So we decided to explore a bit more, and this is ongoing work now. We decided to explore a bit more using this visual representation learning architectures that raised in the last year that use contrastive loss, and then use clustering as a downstream task. So here, again, we're doing in 2 steps, but this is a discussion that is really contemporary in the machine learning community. So we're using the same framework to approach crop classification. And here we propose to use the Xinjiang architecture that was released, I guess, on March or April this year. So it's a very recent one. And we modified slightly the loss function that we have by just adding a margin schema, pretty much inspired in deep k-means. And with that slight modification, we managed to get much closer to the supervised results. And here we also use a much better encoder architecture. So the supervised method got around 90% of F1 score. And the best distance, contrastive distance that we have for comparing similarity in this model, we achieved 85.6%, which is much, much closer. And it's already a reasonable, a decent performance for considering that we have no label in the data set. Of course, this is only for classes. When we get the 11 classes, and so a very imbalanced data set, then the performance drops also for the supervised, but the distance is bigger for the supervised too, because it's also a more challenging scenario for unsupervised methods. And then in parallel, we wanted to approach that crop classification using learning from label proportions theory, and how would that apply to culture again? So we have this paper on the stars from last year, where basically we studied how to use crop proportions from a different source of data. Like in Brazil, we have this census ministry where they collect information about seeds, so we can estimate more or less what would be the proportions of crops in a given area in that year. And we use that information to validate generalization of trained networks with using a much smaller data set training data. And here we wanted to evaluate the feasibility of using this crop proportions data to actually perform the whole classification. And then we are trying to build on this learning from labor proportion theory to do that. And for that, we use this this very nice framework that was published by Caron and all in the RIPS 2020. And it is basically a modification of this usual Siamese networks that instead of we just have in the Siamese networks, usually we have input data, we have a transformation bank that we can source some transformations for that. We generate variations of this input data, we feed to a given encoder, get the features, and then we compare the features in the latent space, considering that since they are generated from the same image, they should be close together in the latent space too. But here, what Caron proposed is that actually, instead of comparing the features itself, they compare the projection of these features into what's called prototypes. And prototypes are basically landmarks in the latent space. So they are analog to cluster centroids. And the codes, so the assignments of these features into the these cluster centroids or prototypes would be compared in the latent space. So instead of saying that similar images should be close together in the feature space, they're saying that the assignment of the clusters should be similar for images in the same feature. So it's a bit more robust in some way. And then basically, here's the assumption. This is another detail that is important to talk about this method, is that they use this swept contrastive learning, where basically they have the transformed images, yes and ZT from a given input image. Then they have the linear layer that would project it into the prototypes, and they have this code QS and QT. And they actually compare, the loss is actually crossed. So they compare ZT with QT and ZT with QS. So they are cross swept. And what they assume is that they should be similar if the image came from the same, the views came from the same image, so they should be similar anyways. Here, just for us to understand, because it will be important for the work I'm going to present, this is how the optimization happens in Swag. So we have two transformations selected randomly using multiprop. So we have two views, X1 and X2, or two variations of the same image. Then we just find the codes of the features using the encoder we have trained so far, Z1 and Z2. And then finally, we compute the codes and the losses. So given a prototype matrix C and the features that we have, Z1 and Z2, we compute actually Q, which are the codes, using the optimal transport with this equipartition constraint. So optimal transport is basically computing an assignment to the clusters, considering that each cluster would have more or less the same amount of samples. So this is the equipartition constraint. And then the loss is computed using that swapped loss that I showed before, which is basically the cross entropy between the codes that we just computed like that, and this PT. And the PT is basically the projection of this feature in the prototypes that we have. So in the end, when we optimize that, we compute the loss and update C and theta, what we would have is an encoder that would generate features that would resemble what we would get if we have this optimal transport optimization for assigning the samples to the clusters. So that's more or less the idea. The optimal transport is more or less guiding the optimization of the encoder to derive that equipartition of clusters in the latent space. And then what we proposed, and this was submitted to AAAI, we just got this week the reviews. I think it's going to be accepted. The reviews were good. And basically what the algorithm is pretty much the same, but we proposed here in this step to modify the optimal transport, which is implemented using this sync-harden-up function. We propose to modify this function instead of using equipartition constraints to use a known proportions constraint. So now the clusters would not have the same amount of samples assigned to it, but they would have a proportion that is known assigned to it. And then, of course, this is important for crop because it's almost impossible the crops have exactly the same amount of samples in a given area. But using information of the crops proportions, we can make the clusters have more or less the confirmation that we would expect them to have. And then we tested that with Cypher 10 and Cypher 100. And for Cypher 10, which is the closest amount of samples that amount of classes that we would have for crops, we got very, very, very competitive results compared to supervised. So supervised, we got 93.6% of accuracy. And using our this methodology, we got around 90.9% in the best case. So it's getting really, really competitive. For Cypher 100, which is a much more challenging case for clustering, then the difference, of course, is bigger also. But still, we got 66.5%, which is a fair result for clustering, considering they have no individual label in this case. So now changing topics, I'm going to talk a bit about climate change and more specifically about weather generators. So how to control synthesis of climate data by inspecting latent space that we would learn using variational encoders. So in this case here, we have this data, which is with weather fields that could be, I used precipitation data, but it could be temperature or other data that we have. We use this chirps dataset, which is a public dataset too. But basically we have the data is this bounding box, geographic bounding box that we have this X dimension and the Y dimension and a temporal window. So it's time series. I use 32 as I meant to present, but it could vary that. It could be a week, depends on that. But it's important that we get all together the spatial and temporal dimensions because then we would model better and more inherently the spatial temporal dependencies that we observe in this kind of data. And then what we did is that we used this variational encoder to find the latent space distribution. And since we were interested on weather generation, so synthesis of data, it was important that we know what is the distribution in the latent space so we could sample from that. Because otherwise, in standard autoencoders, we have a lot of white space where we would basically synthesize trash, and we don't want that. So here we have two losses too. We have a reconstruction loss, which is usually the MSE or the binary cross entropy, for instance. And we have this regularization loss, which is basically the Kullback library divergence of the parameters that we are learning, and a normal with mean 0 and standard deviation 1. So basically, when we train it, we will have the Z to follow more or less the normal mean 0 and standard deviation 1 distribution. And then what we really wanted to answer here is whether we could control how extreme the synthesized climate data would be just by choosing where to sample in this latent space with a known distribution. So the idea is that we would have this latent space with the known distribution, we have a sampler, and then we would generate Z's that we would know more or less what the how extreme the climate event associated in the synthesized data would be. So the first thing that we needed to understand is to build a hypothesis again. So how did we expect climate events to be distributed in the latent space, considering a normal with 0 and mean and 1 standard deviation? So what our assumption here is that very common climate events would necessarily be located near the distribution mean, so at the bulk of the distribution, because there is where they have space to be, more space to be, and since they are a majority, they should more or less be there. And then rare events necessarily need to move towards the tails of the distribution, and this creates locky in the distribution that we can use a sample and synthesize data with known characteristics. And another thing is that, and this is an assumption that might be a bit polemic, but we are also assuming that extreme weather events are also usually rare. And this is, if you consider a small space, this is more or less okay to assume. For instance, if you're looking to a desert region, then a slight rain will be an extreme event, could be an extreme event. But of course, in a grassland, this wouldn't be. So in a local configuration, it's more or less okay. It's a good assumption. So this allows us to have this schema where we have latent space, we have a sampler that we decide where to sample considering the standard deviation, and then we can use the train decoder to synthesize data with different levels of extremeness. To test that, we use this monsoons dataset in Palghar, Southwest India. And this was important because monsoons in India, they have more or less this normal distribution shape of the total precipitation in the month. So we would expect this to be a good example since we have a single distribution in the Latent space, which would be normal shaped. Then the pattern should be of the data should also have more or less a normal distribution. And this seems to be a good shot for us. And then we use basically only the data from 120 to 300 days in this period where the monsoons happen. And then we sample at random several sequences of 32 days, considering more or less 1 degree per own degree with a resolution of 0.05 degrees. So we have 39 years of data to do that. We selected 30 from 1981 to 2010 data for training and 2010 to 2020 to test. And then we did just what I said. We have latent space. We defined some ranges of the standard deviation to select samples. So Z between 0 and T1 would be the bulk. Z between T1 and T2 would be some middle range area. And Z bigger than T2 would be the tail. So the more extreme events would be at the tail, and the more common would be at the bulk. And then the visual inspection of the results, what we got was basically this, and it was quite okay for us. So we have 4 days here with that we selected at random for precipitation. And then we have the real data that was randomly selected. And of course, since it was randomly selected, the most likely is that it was selected from the bulk, the distribution. The more common events will be selected. And then here we have the synthesized data considering different standard deviation ranges. So in the negative tail, we really got the events with lower precipitation values. And then it was increasing towards the more extreme events tail, where we got much higher precipitation values patterns. And at the bulk, we got patterns that were more or less similar to what we get by randomly selecting in real data set. So this was nice to see. Of course, we don't have any commitment to have extreme at the positive, more extreme at the positive tail or less extreme at negative. It could be the other way around, but in this case, it was organized like that, and it was fortunate. Then to evaluate a bit more numerically these results, we have this quantile plot here, where basically in the horizontal axis, we have the quantiles for the real samples distribution. And in the Y axis, we have the quantiles for the synthetic samples distribution. So therefore, this is for the testing set. Of course, if they're exactly the same, distribution is exactly the same, we would have this red line in the middle forming 45 degrees. But of course, they're not exactly the same. So the synthesized samples would differ a bit from the actual testing samples that we have. But one interesting thing that we observed is that the dashed lines here, they are basically samples selected from the test sample, considering some criteria. So we selected 10% less rainy samples, considering total monthly precipitation as the blue dashed line, and then the 30% less, the light blue line, dashed line, and then the 10% highest precipitation samples as the red dashed line, the magenta is the 30%, and then the average would be the green one. And then what we got for the synthetic data set is that when we selected from this ranges, considering only the standard deviation, we got the curves to be almost matching these. So we are really able to control the the amount of precipitation of the synthesized samples just by selecting different loci in the latent space. So that was nice to observe, and we are using these results to do other stuff now. Well, but one thing that we were also a bit worried about is that this works well when we have a single system generating the patterns like the monsoons. But what would happen if we have more than one system in this case? It would probably work well, because we would force this very different system that synthesize data to join together in a single distribution, and this would probably create deformations in the synthesis. So one thing that we wanted to investigate is what would happen if you could just get, instead of a single distribution, to get several distributions at the latent space, each of them following a normal distribution. And to do that, basically, we did more or less the same theoretical background that we used in SWAP. And here again, the main task is to find these optimal centroid positions in the latent space to get the samples to cluster around these optimal landmark positions. But we want also them to follow a known distribution, normal distribution. Then basically, what we did is that instead of having only an encoder, we have an encoder-decoder, and then we get this Latent representation. We have the reconstruction loss, but we also have this loss for finding the prototypes. They are related to the prototypes, which are basically the same that we saw for SWAV. So we have this the cross entropy between the codes assigned using optimal transport and the projections of these samples features to the centroids. And beyond that, we have also this loss for regularizing, but basically we get all the samples that are selected for a given cluster. We compute this MMD, which is something is a competitor of the back library divergence that is basically forcing the features of these clusters that was assigned to a K cluster to follow a normal distribution centered at the prototype coordinate. So we're basically making them not only to be assigned to that cluster, but to follow a normal distribution. And then we get some results here. So here we have some TSNE graphs for MNIST. And when we increase the number of prototypes, we can see that the clusters are really well conformed in the latent space. And when we sample random noise around each landmark, we can really see that they are all about the same digit. So it really happened what we expected. They were clustered by similarity. And this is a nice finding for other applied stuff. We just submitted this paper to ICLR. Next week, we're going to receive the feedback. So we'll see how it goes. And for Cypher, which would be something closer to our kind of problem, we got this very nice result, which is basically when you have a single prototype, we have this image that doesn't tell much about anything in the data set. When you have two, then it's interesting that the data representatives, it's like a bright one and a dark one when we synthesize the prototype centroid. And when we have 10 prototypes, then we begin to see some patterns, which are basically relationships between the background and the foreground. So I have this blue sky and this green like brass structure and something in the middle that would be the object of interest. We have also this grayish bottom part and this light blue sky or something like that. We have some that are green or brown that are probably related to animals or something like that. So it begins to be interesting. And then when we have 30 prototypes, then we begin to have a lot of patterns that are probably the average of some group subgroup of the training set. And how that applies to climate dating again. So basically what we want to do is that we want to get this weather fields time series to pass through an encoder, and then we would assign them to different clusters. And we would expect that they would be clustered by some similarity criteria that would probably be linked to how extreme the event is or this kind of stuff. So we could use that for automatic weather events categorization to improve the weather generator control. So we could synthesize from one of the distributions, and it would only synthesize with samples with that characteristics, considering the data representative we have. And of course, this is a very nice space for investigating the spatial temporal correlations among different clusters, and therefore among different patterns in our training set. So switching again of topic now, I'm going to talk a bit about forest monitoring. And in this case, I'm going to talk about multitask and active learning, considering that I have very small training set. So in this case, we have this data set that's from Brazil, Santa Catarina, and we have this forest area here, a hyperspectral image with a drone. And basically we have this very small training set, but very accurate. So someone was there and say, okay, this one with the GPS, say this tree is from that species, and the tree crown area estimated is more or less this size. And then they just got the polygon around that as a post-processing data. But we have a very small training set. So we have 14 species identified in that area. And the ITCs, they are basically some are only 2 samples. So it's very, very small. But what can we do with that data? I mean, since it's very accurate, we wanted to do something with that. Then for creating the training set, we use this random crop around the samples that we had with a constraint that it should have at least 10% of the polygon should be of a tile image. And then we managed to create a much larger training set just by selecting at random the coordinates and the corresponding masks to segment the trees. And then what we wanted to investigate here was this multitask network where we would compare how much we could improve our performance by adding this new branch here. That is basically a regression task for the tree crown size. And this is actually, I mean, we saw there was similar stuff, so we decided to apply that for this very small training set to see how it goes. And here, of course, we have this this branch for the segmentation following this categorical cross entropy. But here we added also a focal loss here. So we have this gamma parameter for a focal loss, which is basically important for very imbalanced data sets like ours. And we have also this partial loss component here, where basically we are only considering the loss for the pixels within the mask. So we saw that this improves the results for very imbalanced data sets. So we are also using it. And of course, for the regression part, we computed the distance map for a given mask, and then the output should be should have more or less the same distance map. And then we are applying also the partial loss here, but then only to the distance. So basically the MSE error for this branch in our multitask. And the results are nice. We managed to the results for the single track for the convolutional network were already fair, already okay. But adding this task for the regression, we managed to improve, and observing the dividing plots, we can see that it is statistically relevant. It's not only some shift on that. I mean, it's really better. And compared with other methods, then the results are much better. Even the single the task for the convolutional network was better, considering this partial loss and the focal loss compared to previous CNN that we saw in the literature, SVM or rainforest. And then one thing that we did in this paper that was interesting is that we were able to get a label to all the forest pixels present in the image, and we could compute the proportions of species to check with the expert if they were consistent with the expected for the region. And they were more or less consistent. But one thing that was bugging us in this paper is that in this case, every valid pixel would be assigned to one of the classes that we used. And of course, this makes the pixels belonging to a mapped species to be erroneously count for one of the classes that we have. And then this made us work on this other active learning approach. And we are basically using the byproducts that we have from this approach. So we have, when we look at this map estimated by this approach, we can see that it managed more or less to find blobs at the individual trees that could be used for selecting samples and implement episode labeling approach to this active learning framework. So we could identify individual labels better and disregard the ones that are not really important for the model. And then we propose to use this pipeline. This is ongoing work too, where we have this small initial training set. We would train, test the segmentation multitask backbone. We would have the class probabilities for each class and the regression maps. We could combine them to select tree candidates by thresholding, for instance. We would select valid trees out of it, and then we would add these valid trees to a tree inventory. We would compose our population of trees in the end for that area. We could select some samples for a new training set, and we would run that in iterations until the tree inventory converges, stops growing, or the error that we have for the training samples begins to drop. The accuracy begins to drop. So here's basically what we did. We have the input image, then we have the regression map using that training network and the probability map. We combine them by summing. And then for selecting the tree candidates, if we use only the probability map, this for class 3, for instance, then we would have all of them connected together. So this is not a good environment for selecting tree candidates. But when we combine this both, the regression with this probability map, then the threshold begins to separate the trees, and this is a much better environment for selecting individual tree candidates. With this map, we basically filter these individual trees, considering only objects with a reasonable size. Reasonable size here is something that is, of course, an expert knowledge that we embed here. So we know, the expert knows that some species have tree crowns with an average size and a given standard deviation. And we use that information to just get away of spurious noise and trees that are erroneously connected in this kind of stuff. Then we apply the convex hull to these results just to be sure that we are getting all the borders of the trees. And of course, we discard the samples that were already present in the initial data set. Then we have a new set of individual tree candidates that we will add to our tree inventory. And we also subsample from this set an amount of trees for each class, so we can add to the training set. And we do this subsample just to have a more stable training, considering that some trees are much more present than the others in the data set. This is an interesting result that we are having. We're very excited, but we are still running the experiments. And we can see here's the amount of trees for each species that we have in this area, and the total here divided by 10 for the 10 species that we're considering. And we can see that we are really managing to increase the number of trees for that species, that for each species here. Some are already converging, some are still growing. We run only 13 examples so far, but we considering the criteria that they have for thresholding, it's all trees with high probability according to the model. And then at the end, we will see if the proportions are more aligned with the expected of the experts, which would point as an evidence that they could be correct. And here's just as a visualization, here's the output of the first model. We got already much more trees, but of course, the one that is more present is also, the result is also with a lot more samples for that. But then when we begin to iterate, then we begin to populate that area with trees. And we are disregarding a lot of area that is for modern species or something like that. And we have that for 13 rounds so far. And then one thing that's probably one thing that we need to discuss and to better evaluate is how to set up a good sub-criteria for a method. So one thing could be to wait for the inventory to converge, stop growing. And the other ones to always keep track on the accuracy of the training samples we have. And when that begins to drop too much, then we could stop. And we can see that the accuracy for this, it begins to drop. The F1 score is still more or less stable. The average class accuracy is still more or less stable, but probably the classes that have more samples, they are beginning to suffer a bit. So we need to define a good sub-criteria for that. So to finish, what's next with this that are presented? Concerning agriculture, we wanted to explore a bit more unlabeled toxification data, not for crop classification, but to check if you could estimate yield. This would be very important if you could estimate yield for crops without labels. For climate, as I said, we wanted to investigate automatic climate event categorization using the prototypical variational autoencoders method. And this is also something interesting that you want to do is to crawl for small-scale climate connections using this Latent space. Climate connections are basically when you have two climate events that are in different space and time. So, and we are assuming that the event in space A would trigger the event in space B after some time. And we have that for like El Nino, it's this large-scale climate teleconnection, but we wanted to see if we could investigate this small-scale climate connected regional climate teleconnections using the Latent space, which would be a more efficient space to do that. Then the automatic forest recovery evaluation. This is basically we have some data sets, and basically for areas that would have been deforested and now they are being recovered. And we wanted to use this method that we use for evaluating the cover quality, and also to investigate stealth deforestation processes like illegal logging. They are interested in some species specifically, so we wanted to see if this could be applied to this kind of problem. And then, of course, combining climate and forest biomes interactions using Latent space, using both data projected to a common data Latent space to see if we could investigate interactions and also the climate change effects on agriculture, for instance. Yeah, that's it. Now I'm open for questions and comments. Thank you for your time so far.
Okay, thank you, Dario, for this very interesting talk and a very nice example you presented to us. So there's still time for questions from the audience. Either just unmute yourself or write in the chat. So if there are no questions at the moment, I would have one. And going back to your first example, the unlabeled agriculture classification, I'm wondering, so I think for crop type classification, we have a very good knowledge, and normally there are quite a good set of labels. But how easy is this to apply this the method you presented to us to apply this on different domains, for example, where we don't have actually valid labels like the polar regions for classification of different types there? Would this be possible, or would this be difficult because of defining the prototypes?
Yeah, I think it would be probably possible. Of course, we need to have some expert knowledge to define what is the expected amount of classes there at minimum. And if you're going to use proportions, not clustering, but learning from label proportions, we would also have to have this information. So what is the amount of area assigned to each class that we would probably have? Because the model would try to fit to that. So this kind of expert knowledge we would have to have anyways. At least it would be interesting to investigate if we could find like the E in the k-means, that if we could find also the optimal set of clusters, but so far we haven't investigated that. So we consider that we know at least the number of classes that we have. But of course, this could be a following step to investigate also the number of classes. This is the usual thing with clustering. So
yeah,
we could also
great.
try.
Yeah, thanks.
Okay.
Yeah. Hi, I'm Ivica. I also have one question. So with the first approach that you presented, so autoencoder and then k-means. So how do you choose the number of clusters there? Yeah,
so this is given also. It could be in the paper, in this paper specifically, and also in our paper, we knew the number of clusters, right? So our hypothesis was that it was 4 clusters. But we could use this, if we didn't know, we could use this of the covariance of the clusters to basically evaluate the optimal number of clusters. So this is something that we usually do, but in this paper we did. because we use classes.
Okay, yeah, I'm asking because I also am working I did some experiments on clustering for crop type classification. So from a certain feature embeddings from a certain layer of the network to try to cluster them, and then I figured out it wasn't so easy to pick the number of clusters because like if you set it to the number of classes, usually you get really mixed up clusters. So.
Yeah, that's true. One thing that you could also try is to use this prototype thing that would generate necessarily the clusters, and then to investigate how the clusters are close together or far away, because maybe you can join clusters or split clusters and have a post-processing step. So this would be also possible.
Okay, thanks a lot.
Okay.
Okay, any other questions from the audience?
Hi, thank you very much for this super interesting talk. I had a question regarding the modification that you proposed for SWAP, basically the fixed proportions when you do the cluster assignments. I was just wondering, like, how do you select these proportions? How do you set them? Is it manual thing?
Yeah, so we are just the proportions are known. So we are just setting in this case that we know the proportions for that. Because of course, otherwise, if you would compute the proportions for each bag, then you would know the classes already, and there's no point of using that in supervised fashion. So we fix the proportions. So this applies only to problems where you know the proportions beforehand.
Okay.
So this is something important. But one thing that is good in this is that the usual LLP methods, they use bags, proportions, and you need to have some way of measuring the proportions in these bags. And in this approach, you don't need to have that. So this we already have a paper that I didn't present using GAN LLP, where we had a generator of samples where we knew the bags proportions, because in that method it's important. But in this one, it converges without that. So I have only a single proportions, and we consider that we're only sampling from that. So in average, they should respect proportions.
Okay, I see. And so this modification did not influence, let's say, for example, the collapsing problem, or like you didn't witness more collapsing because of this change?
Yeah, no, not much. I mean, of course, depending on the bag size, this could be the relationship between the amount of classes and the bag size. This could be a problem. But since we are dealing, you can even observe that for Cipher 10, we suffered a bit in bag 128. With that, you can see that the performance in one of the configurations 72, and this is more or less related to that. But if you can always increase the bag size or decrease to adjust a bit to the amount of classes you have.
Okay, thank you very much.
Okay, thank you for your question.
Okay, are there any further questions? So otherwise, I think we can close here. I again thank Dario for this very interesting talk. And if there are common interests or whatever, everybody please feel free to reach out to Dario and stay in contact with him if you're interested in his research and in his topics. Okay, great. Then
thank you very much for your time.
I wish you all a wonderful Friday, and stay healthy. Bye.
Okay, bye-bye.